The problem statement from GATE Physics 2011 reads as follows. Which one of the following statements is correct for a common emitter amplifier circuit? Option A, the output is taken from the emitter. Option B, there is 180-degree phase shift between input and output voltages. Option C, there is no phase shift between input and output voltages. Option D, both PN junctions are forward bias. This is a multiple choice question with one correct answer, and we are required to find the correct one. A quick overview of the bipolar junction transistor, or the BJTs. So it's a transistor, which means a third terminal will control the current flowing between the other two terminals. And junction, because it's made up of PN junctions, just like a diode is a PN junction. In the BJTs we also encounter PN junctions. Bipolar, because current is flowing both due to the electrons as well as holes. So there are two flavors depending on the how you arrange the PN junctions. One is NPN BJT and the other is PNP BJT. We'll focus only on NPN BJT for the sake of simplicity. In this NPN BJT, electron is the majority charge carrier and hole is the minority charge carrier. Note again, electron and hole both will contribute to the current. And this is the arrangement for the NPN. You can see emitter is N plus, it's heavily doped. Collector is N type. Base is very narrow, it's P type. And this is the symbol. The arrow will flow from the arrow will direct from base to emitter. This denotes an NPN, and it's vice versa is the case for a PNP BJT. So this is the BJT that we saw, the NPN BJT that we saw earlier. So you can see this is the NPN BJT. This is the collector, base and emitter respectively. And you can see the current flowing, and we have applied some DC bias VVB and VCC. The key thing to note in a common emitter configuration is that this emitter is common to both the input side and the output side. By the way, this is how an amplifier, this is how a black box of an amplifier will look like. So there will be an input side and there will be an output side. So we'll feed some signal, a small signal you can see over here, and this amplifier will amplify it to a larger. So in this case, current is being amplified because we know beta equal to IC upon IB for a BJT. That's what's happening. A small current will amplify to large current, and correspondingly voltage, if we you know that voltage equal to I times R. So voltage V out can simply be IC times RC, the load voltage over here. So if we amplify the current, the voltage will also get amplified, and these are the DC biases, and plus we are on top of the DC biases, we are giving an AC input signal which we need to amplify. And since emitter is common, you see the emitter is common both to the input side, this is the input side, and this is the output side. Emitter is common to both the input side as well as the output sides. Hence, this is configuration is known as a common emitter junction. And usually we ground this DC ground for simple analysis. Right, so this is the circuit diagram for a common emitter amplifier. But first we should make sure that we bias it properly in order to behave it in order to use it as an amplifier. So what do I mean by that? So in this diagram you can see four distinct regions. So I'll try to point it out one by one. So just focus on the cutoff region. So this is the bottom region in the orange over here. In this case, the base emitter junction is reverse bias as well as base collector region. So the source of electrons is the base emitter region. If base emitter is itself reverse bias, there will be very less amount of current. So hence this is the cutoff region, right? The regions of interest, of primary interest to us, when we are operating in amplifier mode, you want to be operating in the active region. Do we mean by the active region? Active region, base emitter region base emitter junction is forward bias. So this means there will be a large amount of, there's a huge supply of electrons from emitter to the base. Okay, so recall that this is how we saw that this was the emitter and we had a narrow base and a collector. So what will happen is that huge amount of electrons will be injected, and if we reverse bias collector and base, and those electrons will quickly cross the base and will go to the collector, and hence the current can flow. Hence in the active region, base emitter is forward biased while base collector is reverse biased. So this is the region, in the big region that you see in them between lines B and C. Between point A and B is what is called the saturation region. So this is where switch is, this is where an BJT is operated as a switch. No, the current is high and the current is low here. This is like a switch on and off. But for amplifier, we need this behavior. A decent amount of current, a constant amount of current which does not change much. So this is the region that for amplifier active region is required, and for this is the, so base emitter should be forward, base collector should be reverse. Now this is again a simplistic diagram of the same BJT. So what you want to do is that I want you to just, if I apply a KVL sorry, along this line, so I can write V plus minus ICRC, let this current be IC, minus VCE equal to 0, and let this be the ground. Okay, so if I rearrange the terms, note that y-axis is IC here, so, and x-axis is VCE, so I write those terms here. So I can write, I'll take ICRC to the other side, so ICRC equal to minus VCE plus V plus. Okay, now I can write IC equal to minus VCE over RC plus V plus over RC. V plus is usually a constant. Okay, so I'm going to write it y equal to minus 1 by RCX plus some constant K. So you can see y equal to minus mx plus C, right? This is a constant. So how will it look like? It will look something like this. So this is VCC over RC, or V plus over RC, and the intercept on the x-axis would be VCC, which you can clearly see here. RC and RC will get cancelled. This is what is known as the load line, and the intersection of this load line with one of these curves will give the operating point or the quiescent point. So for instance, let's say I want to bias it in such a manner that I want to be here. Usually we want to be in the center, close to the center, because so that the swing can be large. If the bias point is taken as over here on this side, you cannot amplify the voltage, because it will go into the saturation region over here. We want to be near the middle for good voltage swing. So by the way, the intersection of load line and one of these curves, it what gives us the quiescent point, also known as the Q point or the bias point. There are different names for that. So that was the DC analysis. For AC analysis, what we are going to do, we are going to model this. We are going to replace this with a simplistic model. The small signal model is what it's called. So we'll replace this NPN BJT with this, and correspondingly, this was the circuit diagram for a common emitter amplifier configuration. And if we replace it with this, and we also short all the independent voltage sources. So VBB and VCC were independent voltage sources. You see they are missing here. They have been shorted, potential 0, and all the independent current sources are open. There are no independent current sources. This is a dependent current source. Note that this is dependent on IB, the current flowing through this branch. And now we'll try to calculate that what is the value of V out for a given V in. Essentially, what I'm interested in finding is gain, which is denoted by V out over V in. What is this value? Again, I'll just simply ground this. So what I'll do, I'll apply Ohm's law. So first I'll apply Ohm's law across R pi. Okay, so if I do that, I'll get V in minus 0. Note this voltage is 0, equal to IB times R pi. So I get V in equal to IB times R pi. Now I apply Ohm's law across RC. If I do this now, I'll get, so current is flowing in this direction, mind you, like this. So I'll get V out minus 0 equal to minus IC times RC. This is the expression that I get. I get V out equal to minus IC times RC, and note that I can simply say IC equal to beta IB. So let's replace that here. So I'll get minus beta IB times RC. Now if what I needed was V out over V in, right? So V out, the value is minus beta IB RC, and V in is IB times R pi. I'll get minus beta RC over R pi. This is the gain, the AC gain or the small signal gain for this circuit, right? So this is the gain that we get. Beta is a positive quantity, RC and R pi are both positive quantities. So what this means is that V in and V out are out of phase. If V in rises, V out will fall. Hence, so this is also known as out of phase or 180 degree phase between V in and V out. You can clearly see there's a minus sign. So alternatively I can say V out is V in plus 180 degrees. There's a 180 degree phase shift. So this is the complete, and this is the gain expression, by the way. So we saw that the output is taken from the emitter. No, the output, if you see in this slide, the output is taken from the collector side. So output is collector and input is base, and emitter is common to both. So option E is incorrect. There is a 180-degree phase shift between input and output voltage. Yes, we just derived the expression. This was the case. No phase shift. No, this is 180-degree phase shift. Both PN junction are forward bias. We saw that this is not the case. So for forward active region, we need base emitter as forward bias, and base collector as reverse bias. For amplifier, this is for the amplifier configuration, which we saw in the DC analysis. So this option is also incorrect. So only option B is the correct one, and that will be our answer. Thank you for listening.